For this week, we're covering research hypotheses, and we're going to go to town on it here. First, I'm going to talk about what the goal of statistics are, and then I'm going to talk about confidence intervals, and then we're going to go into hypothesis testing using the standard normal distribution at first, okay? So our primary goal in statistics is to make inferences about the population. So we call statistics inferential statistics. Statistics are to sample as parameters are to population. So statistics are used to estimate population parameters. The population parameters are generally unknown unless, of course, we're doing something like an SAT test where we have all the data and we know what the population mean and standard deviation is. But generally, we don't have them. But just for now, let's we'll cover that more later. The sample mean is an unbiased estimate of the population mean. So that's a good thing, right? So when I say unbiased, it could be either a larger or smaller than the population mean, so it's not biased in any one direction. If you're interested, I do a proof of that here, a million proofs everywhere. I did a lot of proofs of the normal distribution. Okay, let's take a look at the sampling distribution of the mean. This is going to come into play as we move forward. If you'll recall, the population values have Greek letters and sample values have Latin letters. That's really dark today. It's just, if I face the window, my face will be occluded by the sunshine. I don't know if you care to see my face or not, but it's nice to see a human talking, right? So here's the population, and the population itself, we're assuming a standard normal distribution. If you recall, standard normal distribution has a mean of 0 and a variance of 1 or a standard deviation of 1, whatever you want to say. When we collect samples, we collect samples from the population, and the samples will be all over the place because even if we don't do what's called random sampling, we generally, when we pick samples, we are in a sense picking a random sample because we are where we are for whatever reason. But in general, if we look at the history of humanity and the history of our existence on Earth, it's kind of random anyway. So these samples come anywhere. So this population represents some variable, say like something like happiness, right? So you know, these people would be excessively happy, these people would be excessively sad, and then most people are going to be falling around the mean, right? So these are samples. They could be sample sizes of 20 or something like that, or 30, right? They're going to fall everywhere, and it just so happens that on one day you may pick this one, or you may pick this one. So that's why we have when we do data collection, we have to do repetition of studies because you never know where the sample's coming from. The mean of all the sample means, so again, let's say we're calculating the mean of each of these sample means. The mean of each of these sample means is the population mean, right? The standard deviation of all these sample means is the standard error of the mean, has a special name, right? Standard error of the mean, and it's the standard deviation of the population divided by the square root of the sample size. Okay. So this idea that it's inversely proportional, the standard errors of the mean is inversely proportional to the standard error. Sorry, the sample size is inversely proportional to the standard error is really important because as sample size increases, the standard error will shrink. See, it's in the denominator here, so that means the larger the value, the smaller the standard error. That is an important factor in determining something known as power, and we'll talk about that in a second. So one of the things we like to do is calculate confidence intervals. We usually calculate intervals of certain levels of confidence, like maybe a 95% confidence interval. But anyway, it's a confidence interval is an interval in which we believe with a certain degree of confidence that we'll find the true population mean value. Again, we're estimating population means from sample means. So, sorry. Our estimate is what we call a point estimate because it represents one point, right? But generally, we like to surround that with an interval, say, well, this is our estimate of the population mean, but the true population mean is going to be somewhere between here and here. And that's what a confidence interval is. So we surround our sample mean with what's called a margin of error, right? Yeah. And for calculating the margin of error, we're going to use some kind of some z value, some critical value, and we're going to multiply that times the standard error, and that'll give us the margin error. Okay, so let's see, that's something good. No, right? And we're going to do this with different statistics, but this time we're doing with or different distributions, I should say. So now we're dealing with the standard normal distribution. So it's going to be the z value, like you just did earlier, these when you were calculating percentiles, multiply times the standard error. So let's break down this first component because people can struggle with it. When I teach epidemiology, I just tell my students, we're going to do a 95% confidence interval. I ignore this calculation because it's can confuse some people. For you all, I will have you do it. I'll limit it to more practical examples, either 90, 95, or 99% confidence intervals. I was tutoring a student somewhere in California, taking stats from community college, and her professor was like nuts. Can you do a 91% confidence interval? How about a 98%? Things that you would never do, right? But I guess she was just trying to test their limits of their knowledge. So, that's good in some ways. But, I want to stick with things that you'll normally see. You'll see 90, 95, 99%. Rarely you'll see others than that. So, all right. So what we're looking at is for this z value, the z value covers 1 minus alpha over 2% of the sample values. So if I'll show you in a second everything, but basically we're looking at everything to the left, right? To the left of some point, right? Some point. I'll show you in a second. The alpha, so this value alpha, and we're going to talk more about this in a second. That's the probability of a false positive result. That's something you set in advance. It's the complement of your confidence. So if you're doing a 95% confidence interval, 100 minus 95 is 5, right? Or 0.05, right? So we're going to pick our alpha based on what our confidence is, okay? We'll talk more about that in a second. I have some examples here, what false positive means, but you can look at those yourself, and I'll talk about it again in a second, so don't worry about that. So you select your alpha, right? And again, it's going to be the complement of our confidence. Since the interval, so 1 minus alpha would be the complement of our confidence, but you saw in the equation it's z 1 minus alpha divided by 2. The reason I have to divide it by 2 is because the limits of our confidence interval surround our point estimate. So we have to divide it in half. So that's why we divide it in half, right? So one half of the interval is going to be below the mean. The other half is going to be above the mean. Okay. We will use a table to find our values. So let's go ahead through an example, and I have the table that's out of your appendix to show you this. So here's an example, z1 minus alpha over 2 for alpha. So we're doing a 95% confidence interval here. Our alpha is 0.05. 1 minus 0.05 divided by 2 is 1 minus point zero point. I think this should be 0.025. 1 minus 0.025. 0.025. And here we go in 0.975, right? So let's take a look at our table. So here's what the interesting part. We're going to find the value that sits right here, and it's going to cover everything all the way down to negative infinity. Yet you'll see here that I'm only showing you the interval itself, right? But we need this point. We need this point. We don't care at the moment about the interval. We just want this point. This point, whatever this value is, it cuts off the distribution in the upper something, in this case, 2.5%, right? Because we cut it in half, 0.025, and the rest is below it. But between here and here is 95% because up here is the upper 2.5%, down here is the lower 2.5%. There's symmetry here. It's beautiful. So, but we need to find that point, and to find that point, we have to appeal to a table, and the table doesn't say, okay, well, I'm going to give you the values between this. It just gives you the values below it. Okay, so let's take a look at our table. Let's go to the highlights. Where's my table? Uh-oh. I hate this thing sometimes. Let's see. There it is. All right. Let's go to the table. Computer, that is, not anything else. So here we have our table, and our table gives you half of the distribution starting from 0 to whatever the z value is, right? If you recall, with the empirical rule, 50% of all values fall below 0. So whenever we're looking at something to the right of the mean, we just add 0.5 to it in this table. Some tables will give you everything. Again, I chose this because it makes you think through this problem. That doesn't just give you the answer. I want you to learn this stuff, be masters of the universe, right? All right, so we were looking for that a point at which we'd find which would cut off this distribution at so that it covers 97.5% of all values, right? And then the upper is 2.25, right? Or 0.25%, 0.025, or 2.5% of all values. Okay, let's look at that. That took me a second to do that. All right, so 0.975, right, would go from z all the way to negative infinity. However, this table stops at 0. So from here to here is not going to be 97.5%. It's going to be 97.5 minus 0.5, which is equal to 47.5. So we need to find a value that represents 0.475. So I'm looking at this table, and within the center of this table are all the probabilities of going from 0 to that z value. 0.475 is right here. So it's 1.9012345 1.96, right? That's a 6. So I need a 1.96. So 1.96 is the value that cuts off this distribution so that beyond it we have only 2.5%, and below it we have 97.5% of all values. Okay, let's go back here, and we see that that's 1.96. So that value here is 1. You see it's like right about 2. And that makes sense with the empirical rule too, because with the empirical rule, it said that 95% of all values were within plus or minus 2 standard deviations of the mean. 1.96 and 2 are essentially the same. Okay? If you didn't understand that, or if I went too fast, you want to just replay it and go over that again and again. All right, so that would be our upper cutoff, would be 1.96. And you'll notice that I put these limits around, not limits, they're absolute value symbols around them. That's because you're going to have a positive 1.96 that cuts off the distribution right at the upper 2.5% right here. But at the same time, we also need the lower limit, and the lower limit will cut off the distribution at the bottom 2.5%. So it means everything to the right would be, involved, right? So these are cutoff points, and they have to be both positive and negative because they surround the mean. So I put it as, I mean, some people will just write 1.96, but I do the absolute value because the fact is it's both positive and negative. All right, let's do an example here. I think I did this one. Yes. Do Danielsville high school students weigh more on average than high school students statewide? We're using the Rodriguez Weight Index, RWI, instead of weight. Why not? Because heck, it's it's my world and we just all live in it. RWI accounts for height and lean body mass. It's really funny because I'm so against people using their names for things. So I kind of do this as a joke. I would never put my name on something for real. But in a book, I can do it for fun. But there's people who like name surveys after themselves. I think it's so arrogant. We're using the RWI instead of weight. RWI accounts for height and lean body mass, muscle and bone density, that is. RWI scores range from 0 to 100, with higher scores representing greater progression to obesity. Okay, so here's a little bit about that. The RWI has somehow we got the population mean of 68 and a standard deviation of 15 for students statewide. Okay, so we have these population values. Imagine we collect data from a sample of 100 adolescents and their mean RWI is 70. So let's calculate the 95% confidence interval. Okay. So step one, we'll calculate the margin of error. So here it is, margin of error Z1 minus alpha over 2 times the standard deviation divided by the square root of the sample size. We know our sample size is 100. We know from what we just did a moment ago that this critical value is 1.96. We know our standard deviation is 15, so we can go ahead and do this calculation. That's 2.94. Calculate the confidence interval. Okay, so the confidence interval, we'll take our mean and we'll add and subtract the margin of error from it. We get 67.08 and 72.94. So what this tells us is that we are 90. So our point estimate is 70. So that's a good estimate. But given what we saw with this sampling distribution of the mean, may or may not be good. So our point estimate is 70, but we are 95% confident that the true population mean is between 67.08 and 72.94. There we go. Here it is. It's interesting that if the confidence interval, so this is kind of a different thing, and you should know this. If the confidence interval includes the null population mean, which in our case was what, 68? It was 68 or something, right? Yes, it was 68. So that's embedded within this confidence interval. So we cannot say our sample is far away enough from our population mean to indicate that we have a different population in itself, right? One of the reasons we do statistical testing, we want to see if our samples differ from the population. Although these confidence limits are used to tell us whether or not, we estimate the true population correctly. When we're doing statistical testing, we're often more interested in knowing if our sample differs from the population. Like, wow, if, for instance, our sample weighs significantly more than the population, and I'll talk about what significance means, then we could say, maybe there's something that we should investigate here. Like, wow, why are our kids heavier than the population statewide? And then maybe we can do an intervention of some sort. So we're interested in this, but if our 95% confident interval includes the true population mean value, right? Then we cannot say our sample is different. But in general, when we're doing these samples, we may be finding populations of their own. So and then we can do sampling from within that population as well. There's a lot of interesting stuff here. There's a practice problem. Imagine that I collected data on a math competency test from a sample of 40 students. The population mean score on the math competency test is 78 with a standard deviation 9. If our sample had a mean math competency test score of 80, calculate the 95% confidence interval. If our sample different from the the population of math competency, so I'll be using that. That's our confidence interval include the true population mean value using the same information to a 90% 90% confidence interval. So there's some practice problems for you to do, and I'll add all those results I'll add those results to your files in Canvas so you can check your work. So you definitely want to do those. All right, let's move on to the next section here. So I mentioned you can actually test research hypotheses using the confidence interval, where you can compare your sample to the population to see if there's a difference. That was the last thing I just talked about. But when we do hypothesis testing, we generally use confidence or intervals to supplement what we're doing, not necessarily to replace a statistical test. So let's look at the steps in the research process. We ask a research question, we formulate a hypothesis or hypotheses, we select our alpha, we select the appropriate test statistic and calculate the test statistic value, draw a conclusion, and then repeat the study with different samples because what I talked about the sampling distribution. So what's the research question? It's a very specific question reflecting a researcher's belief about what will happen. I think we did some of the first session here. So here's an example from the textbook. Danielsville High School students, right? Their RWI, oh, our sample had a 70 RWI, but RWA statewide population mean was 50 with a standard deviation of 30. So it's a little different than the last example. Research question is, do Danielsville High School students weigh more on average than high school students statewide? Okay, this is important, right? The data were collected before generating the hypotheses, and we saw that our sample mean was higher than the population mean. So when we ask our question, we'll say, is our sample statistically higher on the RWI than the population? Clearly they are, right? 70 minus 50 is positive. It's positive 20. So we know that they are in actuality higher, but that doesn't mean they're statistically higher because again, when we look at that sampling distribution, this could be just some random sample picked from that population. And it just on that day, it could have been higher for some reason, bad scales or whatever. I don't know. So that's why we have to do the testing. So our hypothesis and our null hypothesis, and we write null hypothesis with H sub 0. 0 could mean null, or you want to not the hypothesis you'd like to nullify, or it could mean the difference between our population and our sample is 0, whatever you want that to attribute that 0 to. But it's the one that we want to reject. Okay. So when we write out the null hypothesis, we write something like this. H sub 0 is that our sample mean is equal to the population mean. This is what we'd like to reject. I mean, I just saw that my sample mean was 70 and the population mean was 50. So it looks like it's greater. So I don't want to conclude that it's equal, right? I'm not interested in concluding that it's equal. So my null hypothesis is either the sample mean is equal to the population mean or the difference between the sample and the population mean is 0. Or we could write it like this too. Sample mean is equal to 50 because that's our population. You could write it out as long as you communicate your intent. Our alternative hypothesis, which we either write as H sub 1 or H sub A, you can see it either way. This is our research hypothesis, our wished for hypothesis, what we're hoping to find, right? So if we write it out symbolically, we'd have our sample mean is greater than the population mean. Or we could write it as our sample mean is greater than 50. It's interesting though that this type of alternative hypothesis is directional, right? And it says my sample mean is greater than. It doesn't say that it's less than, it says it's greater than. So we indicate a direction. But you don't have to do that. You can also say that my sample mean is not equal to the population mean. Or there's ramifications to such decisions, which you can read about in my textbook. And I'll hint upon them here too. In every research study, you have these 4 different possible outcomes. So if we look here, we have our decision. And this is the true state of affairs, which we personally don't know, right? If we knew, we wouldn't be doing studies. So if the null hypothesis is true and we reject the null hypothesis, we've committed what's known as a type 1 error. That's what alpha means. If the null hypothesis is true and we fail to reject it or accept it, whatever you want to use, some people have trouble with some of this language. And they'll say, well, no, but technically, but I'm talking about what we actually do as humans. This is our confidence. So confidence, yeah, we're confident that our sample belongs to this population, right? That's why it's confident. They're complements, and we already looked at that. If the null hypothesis is false and we reject the null hypothesis, we've done a good job. We have power. If our null hypothesis is false, right, but we reject the null hypothesis. I'm sorry, if our null hypothesis is false and we fail to reject the null hypothesis, we've committed what's known as a type 2 error. And that's symbolically beta. So power and beta are, and type 2 error are inversely related. So power is 1 minus beta. Beta is 1 minus power. Comes in handy when you're doing sample size calculations, right? Everything's listed here. Ideally, power should be greater than or equal to 0.8. When we do studies, when we usually we plan our studies by estimating our sample size. When we do that, we set our power at zero point 0.8. We don't set it at 0.9 or even 1. Shouldn't it be 100% certainty that you'd reject the null? Well, there's ramifications to that decision too. So we like to use 0.8, 80% chance. Power is affected by sample size. I mean, if you were to look at, if you were to look at the distribution and look at the sampling error of the mean and recalling that our that our standard error is inversely related to the sample size, you're shrinking the error as you increase your sample size, and that has ramifications for power. All right, so how do we select alpha? It's pretty common that people use 0.05 or a 5% chance of falsely rejecting the null hypothesis, falsely rejecting a true null hypothesis. However, it's not mandatory. People act like it's mandatory. Other options include 0.10 to even up to 0.15. You would use these if it's the initial testing phase for something and there's nothing at stake, right? Like for instance, so this is saying having a 10%, even a 15% chance of a false positive result. That would be okay if I'm doing some kind of pilot testing. I'm testing something new, but there's nothing at stake here. Like let's say I'm testing a drug and the drug has potentially hazardous side effects. If I say, hey, the drug works, but in fact it doesn't work, it could kill somebody. So we tend to be more strict when we're dealing with something that's dangerous. We can also use, well, so a larger alpha gives us greater likelihood of rejecting them, right? Of rejecting a false null hypothesis. So we end up having more power too. So that's why people tend to use that, especially when their sample sizes are small. We use an alpha of 0.01 when our sample size is really, really large because it's so easy to reject a, a false null hypothesis to the point where we reject everything. And sometimes we reject things that are not really meaningful. So when our sample size is really large, we tend to shrink our alpha. And we also, if we're worried about the ramifications of this, like I mentioned, that drug test, we could shrink our alpha. We want to be really, really sure. There's always consequences to all of these decisions. Yeah, I'll come back to this. So let's look at our Z. So when we want to test hypotheses, if we can assume normality or we can transform our variable like we just did, a Z value transforms your variable. We did that with the calculation of percentiles, right? We transform values into Z scores, standardized scores, right? That's what, if we do this, we can use a normal distribution. So one of the things I mentioned was choosing your test statistic. If I can transform my values into something normal, then I can use this Z-test. So Z-test is the sample mean. So remember when we did the percentiles, we took the actual person's value minus the mean. Well, now we're dealing with samples rather than individuals. And that's why we have to weight the sample by the sample size. So this is the same as the Z value, right? Z value was X minus mu divided by sigma, but here now we have to account for the sample size and we're dealing with means. So that's the only reason this looks different. right? Sample mean minus the population mean divided by the standard error of the mean. So let's look at an example. So our data on 33 DHS students who completed the RWI, the mean was 70. So research question is, do Danielsville High School students weigh more on average as measured by the RWI than high school students nationwide? It's very precise definition. That's why you should do these research questions. Verbally, the null and alternative hypotheses are as follows. And I say verbally, and then I'll do it in symbols. The sample mean equals the population mean, or the difference between the sample mean and the population mean is 0. Either of those are equal. Alternative is the sample mean is greater than the population mean. In symbols, we have sample mean is equal to 50. Again, I showed you different options here. And then alternative sample mean is greater than 50. Again, we're looking at one side of the distribution, right? So we'd actually call this what we'd call this a one-tailed test. So we select our alpha of 0.05, and I'll explain that when we look at the picture. So this means we accept no more than a 5% chance of a false positive result. This is going to determine whether or not we have statistical significance. So since we have our population standard deviation, we'll use the z-test. Sometimes we don't have it. Like I might give you a hypothetical. I say, well, the population, let's just say that the population mean value is 50, but I don't have any data, so I wouldn't have a population standard deviation. So in that case, we would use something known as a t-test, which we'll cover next week, right? This t-test with its degrees of freedom, which we'll talk about next week. It's a sample minus the mean divided by the standard error, but you'll notice that the standard error has an S rather than a sigma. So we do that instead, okay? So that's what is next. So we do our calculation and we get 3.830. Determine if the test statistic value is different from the population mean. Okay, so we calculated. Okay, so once we have our alpha value, we need to know what our critical value is, right? So our critical value cuts off the distribution. Now, in this case, you'll notice this is different from the earlier one. I think that was in the last lecture. Yeah, half of the lecture. Let's see. Yes, here. Get a better picture. Here. So you'll notice here that when we were calculating the confidence interval, we had minus 1.96 and positive 1.96, right? Because the confidence the interval has limits that surround the mean, right, on both sides. Here, though, in this picture, we're only looking at half of the distribution. Why? Because when I set my alternative hypothesis, I set it at the probability. I was looking at whether or not my sample mean was greater than the population mean. I didn't ask if it was less than the population mean. I asked was I hypothesized that my sample mean was greater, right? 70, I think it was like 70 minus 50 is 20. So that's positive, right? Because of that, you'll see that instead of splitting my population into the upper and lower 2.5%, the entirety of the 5% is on the right side of this distribution, right? The value that cuts off this distribution at the upper 5% is a z-value of 1.645. So how did I find that? All right, so my alpha was 0.05. 1 minus 0.05 is 0.95. If I go into my table here, so I want to know what the z-value is that cuts off the upper 5% of the distribution, not 2.5%, but 5% of the distribution. So again, we have our table shows us from 0 to the z-value. That area would be 45% of the distribution. The remaining area, of course, would be 50%. So I said 95 minus 50 is 0.45. and I look for 0.45 here, and I'm somewhere between 0.4495 and 0.4505. So I'm at 1.60124. So like around 1.645, right? Because it's between 4 and 5. And you'll see people write 1.64, 1.6, whatever. There'll be a lot of different values there. And here it is. I have 1.645. So that's my Z value. Okay. To get to know what I just talked about there, it's really important, not just for my class, but for you to, even if you never do stats by hand again, you need to understand this. This is critical. All right, so where are we? So we did this. So one of the things we want to know is so we need a p-value. We have our alpha. We know what our critical value is. It's 1.645. We have our z value. It's 3.830. We need what's called a p-value. A p-value represents the probability of a value this large or larger given the null hypothesis is true. So if the null hypothesis is true and the true population mean is 50, what's the probability that we observed a value this large, a difference? Because remember, our score was the difference between our sample mean and the population mean, right? Difference this large or larger, and then we converted that difference into a z-score. So what's the probability that we see a z-score this large or larger, 3.830 or larger, given the null hypothesis is true? So we're going to look in our text appendix to see if we can find the probability of a z value greater than or equal to 3.830. But as you know, in our table, we only see the values that are smaller than z, right? So we'll look at the complement here. Now, in this case, I wrote the probability, so 1 minus the probability of z less than 3.830. I could have wrote less than or equal to as well, because this is a continuous variable, and the values can be so small that it can be infinitesimally small. Infinitesimally, I think that's how you pronounce it, small. All right, so let's take a look at this value here. So I did it for you here. So I need to find a 3.830 in that table. Generally, you wouldn't be using a table for this. You'd be going to the book. So I said, what did I say the value was? So I need 3.830. Do we have 3.830 in this table? So we go to 3. Well, we don't have 3.8. This table goes to 3.5. 3.5. So the the largest probability covered in this book is 0.4998. So that's a value between z value of 0 and 3.5 is 0.4998. And if you add 0.5 to that, because remember we're going back to negative infinity, be 0.9998. I mean, it's going to be smaller than that because this is 3.5. Wasn't our value 3.8? Was 3.8, right? Yes, 3.830. So it's going to be less than that, right? So what I do there is I'll just use 0.9998. So the probability that z is greater than or equal to 3.830 is 1 minus the probability that z is less than 3.830, which is 1 minus 0.9998. It gives us 0.0002. But notice I write less than 0.0002. So my probability is less than 0.002. So what this means is that probability of value or a difference as large as we observed or larger. Always have to say or larger, or a probability of z value of 3.830 or larger is less than 0.002. Well, is this statistically significant? So the way we determine that is we use our alpha. So our alpha was our acceptable probability of a false positive result, or acceptable probability of a mistake. We reject a null hypothesis then when we shouldn't have. rejected it. We set that in this case at 0.05. So we want to know, is our value more that we calculated more extreme than that? Well, it is, because if we look at our table here, or our figure, wherever that figure was, there it is. This area here cuts off the upper 5% of the distribution. And our value is like point zero, was 3 point something, 3.8 something. It's going to be like way out here, right? So it's way smaller than our cutoff. That means the probability of our observed result is much smaller than what we allowed. We would accept a 5% chance of being wrong, but our probability of belonging to this population is really, really small. It's less than 0.002. Was it 0.002 or point 0, whatever it was, but it was really small. It was definitely smaller than 0.05. So in that case, we would reject the null hypothesis and conclude that statistically we are different. Now, I say statistically because in some fields, people don't think that's good enough. They want to know if it's okay, it could be statistically different because that's dependent on the sample size. Well, what if our sample size, was excessively large? Then everything would look like it's statistically significant, right? Wouldn't it? So look, think of it, just look at this equation. The larger the sample size, the denominator is going to shrink and the z-value will increase. So large sample size will almost guarantee that you have a significant result. And people in those cases want measures of practical significant, what we call effect sizes. We'll talk about that later. But they may say, okay, well, but at least it's statistically significant. Okay. So these cutoff values that we pick, like the alpha of 0.05, are chosen because we know that there's there is variation in our sample means. Again, some sample means may be larger than the population mean, some could be smaller than the population mean. They're all over the place, right? Let's look at the example of happiness. I like using this example. Let's say we picked a sample. We're measuring happiness in a population. We want to know if our sample was happier than the population. And we pick them the day after, say, the Eagles won a critical game. People are going to be really, really happy in Philadelphia. But what if instead we did our sample on a day when the Eagles lost an ugly game? So people are excessively sad. Those are random events, and they affect our statistical results. So in order to counter these problems, we set our critical value or cutoff so far away from the population mean that we can make these errors, but the probability of an error like that is so small that we'll say, well, we can live with that, even though it's possible that we had a sample on that day that was affected by some random occurrence. The likelihood of that occurring is very, very small. So that's why we set our critical values so far away from the mean, like we did here. And see if do I have anything else here. So we said that's significant. And let's see, anything else I want to talk about here? Oh yeah, and then the next step would be to repeat the study again because of all that's like I said, because these are samples are random, you want to repeat them over and over again. And then I have a practice problem here for you. All right. I would always add a confidence interval to the to the different to the different these estimates, right? So you want to add a confidence, even though you did the statistical test, you want to add the confidence interval to it. And I don't know if I have this here, but I'll talk about it again later. But the thing is that if so, this is a one-tailed test because we're looking at one direction here. But what if I had asked instead, is my sample different from the population mean value? Instead of saying, is it greater than or is it less than? Different means that it could be either greater than or it could be either less than, right? If I did that, then here's the interesting thing. I can't use this Z value of 1.645 because that encompasses the upper 5%. So once I set my alpha, it's my alpha, whether I do a one or a two-tail test. Again, a one-tail test means I'm looking at one side of the distribution as we did here. In a two-tail test, I'm going to look at either side because either my sample mean is going to be greater than the population mean or it's going to be less than the population mean. right? So if I do a two-tail test, I'm keeping my alpha at 0.05. Instead of the 5% being on the top of the distribution as it is here, the upper 5% of the distribution, I have to cut that in half, right? So that I'm looking at the top 2.5% of the distribution and the lower 2.5% of the distribution as we did here, right? So my cut, Piper's laughing, that my cutoff values would be 1.96. Remember we did that earlier where I put the absolute value around 1.96 because this will be cutting off the upper 5% and the lower 5% of the distribution, right? 0.2025 plus 0.025 is 0.05. So we keep our 5%. But what that'll do is that'll move my critical value from 1.645 to 1.96, moving it further away from the mean, making it more difficult for me to reject the null hypothesis. So what's the bottom line there? It's better to do a one-tail than a two-tail test if you can. Doesn't mean it's bad to do a two-tail test. Sometimes it's easier to do that just because you don't know. If I have data though in advance and I see what my sample mean is and I see what the population mean is, why not do a directional test? But if I'm designing a study from scratch where I haven't collected the data yet and I'm not really sure what's going to happen, sometimes it's better to do a two-tail test, right? One thing you cannot do for sure is you cannot run the test and then change it later. You did a one-tail test and you failed to reject it, but if you did a two-tail, you would reject it because that does happen. You can't do that. That's cheating in research. Thank you, everybody. I hope you do great on whatever the next assignment is. And see me if you need help, because some students have been coming to see me and they're actually doing better. All right, thank you very much. Piper says thank you.